So, Mrs. Hochgravy, how would you describe how to draw this next figure?
Well, I noticed that there's two basically rows of blocks or squares. They look like there's one that's a row of 4 and one that comes out of it that's a row of 3 or 3 in a row. So looking at those, I noticed that the strip of 4 starts on its back and then it stands straight up and then it looks like it's the top. So now I'm thinking that row of 4 is going to be what's on the left-hand side going vertically.
Okay. So kind of if I drew
four blocks just right on top of each other.
Okay, so if I drew something like this and then draw the 4 blocks like you're saying.
Absolutely. And then looking at the 3.
Sorry about that, guys.
You're going to notice that our drawings are just super fabulous as you go through this class. Being sarcastic. Okay. Now, the row of 3, notice it started vertically, then it sticks out horizontally, and then it's vertically, but it's below. So now I think it's going to be horizontally, but it looks like it's going to come out of the second from the top block,
so second from the
going
top.
to
so
the right.
This is the first, second right here?
Absolutely.
So to draw 2 more or 3 more?
2 more coming out there.
Okay.
Now, another way to think about that, it looks to me like that figure has been rotated. And I bet, Mrs. Palermo, you could show us what that would look like if we just took that
Great word.
figure.
I'm going to write that down. And guys, this word rotating, you're going to see this. You've heard of it. You've seen it before. We're going to see that later on in the year. So if you rotate, which way do I need to turn it?
Looks like to me you're going to need to go counterclockwise.
So that would be to the left?
To the left.
So if I'm rotated, so
there's our next figure.
There's
Perfect.
the next figure.
And then if we did, so it looks like it's 90 degrees counterclockwise rotation, Mrs. Palermo. What do you think of that description?
Great vocabulary. Whoop. 90 degrees counterclockwise rotating. So if I rotated this one 90 degrees, so went to the left again.
It should get us to that next one.
And then this one, let's test it. So we're going to test our idea, which is basically Mrs. Hochgravy is coming up with is a conjecture. This whole rotating 90 degrees counterclockwise is her conjecture based on her observation, and it looks like we got the figure that she described.
Perfect.
Nice job.
All right, now this is where you guys are going to pause and you're going to go ahead and try the next example, and then we're going to go ahead and continue with this next example. All right, so now, Mrs. Palermo, we've got some sequences of numbers, and we need to be able to predict what's going to happen next, what that next number is going to be in this sequence. And what would you tell me? What do you notice is happening each time?
First of all, do you think I can get a calculator out and test this?
I think this would be a great idea.
Okay, so I'll get my calculator out. And so first thing I'm noticing is that the numbers seem to be getting smaller.
Absolutely.
Or decreasing. But I'm looking at it, and it's not like it's decreasing by the same amount, like subtracting amount. So then I'm thinking, could it be dividing by something? So I'm going to test it and just put in my calculator, 48, and I'm going to divide by 16 just to see what number it decreases by. So 48 divided by 3 actually gets me 16. So if I do keep dividing that, each number, next number, by 3.
Ooh, which that's pretty. That's 16 divided by 3 would be 16 thirds. That's a pretty good idea.
Now, what about 16 thirds divided by 3 again? Would that get you 16 ninths?
Well, it should make sense because we know that dividing by 3 is really multiplying by 1/3.
Ah, so if I multiply by 1/3 as well, then that would also be the same thing as dividing by 3.
Absolutely.
So then my next number then, I would say, would be 16 over 27.
Wonderful.
So if I was asked to describe the pattern, which is Miss Hochgravy asked me to do, I would say 2 things. I could say divide by 3, or, like Mrs. Hochgravy said, you could also multiply by 1/3 because it's the same thing.
Now, in your description, Mrs. Palermo, do you think it would be important to say that from that previous number, divide by 3 to get to the next number? Or do you think that as long as we're keeping that pattern, we're probably okay with a short little
I think so, as long as you're doing the same thing each time. Now, if I was dividing by 3 and then dividing by 6 and then dividing by 9, changing it, then you would have to kind of have some more description words.
Sounds good. All right, now what about this next one? This next one looks a little bit different here.
Okay, so first thing I noticed is that it's not decreasing like the last one. So I notice it's going up. So increasing would be a good word. But I'm also noticing it's not like it's increasing by the same amount each time. And I also notice it's not really being multiplied by, like the last one you could say divide or multiply. So I'm going to just start writing. So it'd be adding 3, and then this one is adding 5, and then adding 7. So right away I'm noticing it looks like it's increasing by odd numbers in a sense. Okay. So then the next one I would say, if I'm sticking with that pattern, maybe I am adding 9. What do you think?
I think that looks wonderful.
So if I add 9 to 17, that would be 26.
So the next number is 26, and that's wonderful. And the way we could describe that would be what?
Well, it was increasing or adding. So I could say increasing by, we were talking about odd numbers, but they're not just any odd numbers. Like 1 is an odd number. So it's increasing by, oh, she's writing the word consecutive. So consecutive means like one right after another. So increasing by consecutive odd numbers, and probably need to say starting with 3, because 1 is a consecutive or an odd number, but it's not in part of this pattern.
Right. So notice here how this is changing. Up here we said we could just say you're dividing by 3 or multiplying by 1/3. But here, because this number that the number that's changing, or the number that's helping you get to the next number is changing, we want to specify with what you need to start with. So starting with 3.
And I love her word consecutive, another good vocabulary. I think the big key is when you're describing a pattern, you want to be as specific as possible. You don't want to, just throw something out there and make it kind of confusing. So be specific. All right. So remember in the notes section, we talked about, again, the word conjecture, our new word. And so a conjecture, again, just to restate, is an unproven statement based on your observations. So what they have here is a statement that is not complete. So we need to complete it. And one of the ways to complete a conjecture or make a conjecture is to provide examples. So here's the conjecture they have started. It says the sum. Now, what does sum mean, Mrs. Hochgraby?
It means we want to add.
So we're going to add, and it says the first n. Now, n is a variable, so n could be represent any number.
Right.
They throw in the word odd, so we already know what odd means. We talked about that before. Positive, of course.
Can't be negative.
Can't be negative. And integer.
No fractions, no decimals.
No fractions or decimals. All right, so we're going to list some specific examples first and look for the pattern. Often what I do is I try to list at least 3 examples. That way I can work with it a little bit more. If you need more, then list as many as you need until you find a pattern.
All
Again,
right.
that key there.
So if I'm adding just 1, because 1 is an odd number too. So 1 odd positive integer. The first 1 is just 1.
Yeah.
So that sum is just 1 because it's really itself. But then if I have 2 odd positive integers, that would be 1 and 3.
So what she's saying is that n, that variable n, she's adding the first 2 positive integers, odd integers. So 1 plus 3, what does that equal?
That would give me 4.
Okay.
Okay, so then if I do the 3 odd positive integers, so yeah, that number I'm changing is the n. So 1 plus 3 plus 5, that's going to get me to 9.
Okay, I'm going to write off to the side kind of what she said. She said, so if n equals 1, so there's only 1 odd positive integer, that was only 1. If n is 2, that means there are 2 odd positive integers that you're adding together. And if n is 3, there's where you're getting the 3 odd positive integers.
Absolutely.
Okay.
And we could continue that. Let's just do one more just so we have it up there.
Excellent
So if I
idea.
did, if n was 4, 1 plus 3 plus 5 plus 7, and that should get me to 16.
So what are you noticing here? Are you seeing a pattern at all, Mrs. Hotegravy?
Well, I do notice that 1, 4, 9, and 16, those are all perfect square numbers.
Oh, so and again, you're looking at the sum. The sum is the final answer to an addition problem. So
And actually, not only are they perfect square numbers, but whatever my n was, it's that number squared.
So the n is 1, so that would make this 1 squared.
Right.
When n is 2, you square that, you get 4. Oh, so you square the n of 3. I see it. Nice job.
So really, to finish that conjecture, the sum of the first n odd positive integers would be n squared.
Awesome. Good work.
All right, now this next one, Mrs. Palermo says the product of any two consecutive positive integers is.
Okay, so product means we're multiplying. So we're multiplying some numbers together. 2, so we're only multiplying 2 numbers at any given time. Consecutive, we talked about that before.
So right in a row.
Right in a row, positive integers. We've talked about this.
Okay.
So it says any 2 consecutive positive integers. So like, I'm going to try to keep it easy. What about 10 and 11? So 10 times 11 equals 110. Okay. What about 4 and 5? Again, I'm thinking of examples, as many as I can. So that'd be 20. What about like 8 and 9? That'd be 72. And I could keep going. What about like 1 times 2? 2. I'm noticing they're all even.
Okay.
What do you notice?
That is definitely true. Now, if there was anything more specific than that, we might need some more examples to take a look at.
Yeah.
And that really is all that there is for any two consecutive positive integers. That product will always be even. And that is the relationship that you're going to see there.
Cool. All right. So just to kind of backtrack a little bit, we talked about earlier about conjectures again, but how do we know they're true?
Well, you know it's true if it's true for every single case. And we talked about how that's really hard to prove with numbers. For example, to prove that the product of any two consecutive positive integers is even, I'd have to list every set of consecutive positive integers, and that's ridiculous. We can't do that.
And so when we made that conjecture on the last slide, we didn't really prove it. We are just kind of basing it off our observations. So
Absolutely.
if we really had to prove it, we'd have to do a lot more work. So what if it's false?
All we need is one counterexample, one case that disproves our conjecture.
So only one counterexample. Seems a lot easier to me.
Example 4 says that we're going to be finding a counterexample. So that right there is already telling us that these are going to be false conjectures, because I will never make you find a counterexample to something that does not have one. So we're going to be finding a counterexample to these conjectures. The first one says the difference of two positive numbers is always positive. So we're doing difference. What does that mean, Mrs. Palermo?
Subtract.
Absolutely. We want 2, so we're subtracting 2 positive numbers. The question is, will it always be positive? Now, when I'm finding a counterexample, I want to take a look at this conjecture. I don't want to change it. I just want to change its outcome. I want to change what's happening in the end. So we're still going to be taking the difference of 2 positive numbers, but we want a different outcome.
So in other words, we want it, we don't want it to be positive, so it has to be something that's not. Could be 0 or negative.
Absolutely.
Okay, so difference of 2 positive integers. So I'm just going to throw out, let's say 4 and 5. So I do 4 minus 5. That gets you -1.
And
Does
that right
work?
there? Yep, because it's not positive, so we're good.
Awesome.
All right, the next one says for all real numbers x, so we're throwing out a variable here, the expression x squared is greater than or equal to x. So here right now, what they're saying is that x squared is greater than or equal to x every time.
Okay.
We want to prove that that's not always the case. So we want to show that it's not always greater than or equal to x. So what would it have to be?
It would have to be less than.
All right, so this is what we want to show. To prove our counterexample, we want to show an example where x squared is less than x.
Okay, so picking some numbers. Let's say 2. That's easy to work with.
So then the 2 squared would be?
So that'd be 4.
and then the
That
x
would
was our
be
2.
2.
So is that true?
No.
No. So actually that proves our conjecture to be a true conjecture, right, for that example, but that we're trying to come up with a counterexample.
But then again, remember what Mrs. Hograby said. She's saying, since it says find a counterexample, this has to be a false conjecture, even though it seems like it's working, right?
And a lot of times when you think about squaring, we think about numbers getting bigger.
Uh-huh.
So let's think outside the box.
Okay, I'm thinking maybe a fraction or decimal. So, and it
Yeah.
says real number, so it can be. So let's try 1/2.
All right, so let's think first of all. We know the x is 1/2. What is 1/2 squared, or 1/2 times 1/2 going to give us?
1/4.
Absolutely. And 1/4 is less than 1/2.
So
there you go.
my x, for this counterexample, x would have to be 1/4. And you just need one counterexample.
1/2. Yeah.
Or 1/2, sorry. You
1/4 would probably work too.
1/4 would, yeah. So there's a lot of counterexamples, but the one I found was 1/2.